So three special types of subspaces are row spaces, column spaces, and null spaces. A very typical question would be to determine the bases for any given matrix of the row space, column space, and null space. The first step to answer any question even remotely like this would be to find the reduced row echelon form of the given matrix. So let's go about with that. So we have 1, 1, 1, 1, 2, 1, 2, 5, 2, 0, 1, 0. The first step I am seeing is this 1 over here. I can turn to 0 by using the first row. So I would apply the very simple operation R2 plus negative R1. That would give me 1, 1, 1, 1 minus 1, 0, 2 minus 1, 1, 1 minus 1, 0, and the rest stays the same, since we haven't applied any operation yet. Recall the reduced row echelon form. We're trying to get all the ones diagonal, and all the leading ones must have no number except for a 0 in the same column. So moving on with our process, I'm thinking getting this one to turn into a 0 by using the second row. So the operation I apply would be R4 plus the negative of R2. That would leave me with 1, 1, 1, nothing to the first row, nothing to the second row. Third row stays the same, but our fourth row is simply 0. We're getting closer. So now I have R3, which I can turn into a 0 of the 2's over here by multiplying R1 by negative 2 and then adding it on to row 3. So the operation would look like R3 plus negative 2 R1. 1, 1, 1, 0, 1, 0, and then 0. Negative 2 plus 5 would give me positive 3. Negative 2 plus 2, 0, and then the last row remains the same. Now I'm trying to get rid of this one over here and trying to turn the 3 over here into a 1. So I would think R3 plus negative 3R2 would give me a 0 over here. So 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0. I now have 2 rows completely filled with zeros. On to what looks like the last step in our process. We're trying to turn this one into a 0 so we can have a column full of zeros and one leading one. So that would mean R1 plus the negative of R2. 1, 0, 1, 0, 1, 0, and the rest, of course, the same. And right there we have half the answer question answered. So this was R1 plus the negative R2. So we have our reduced row echelon form. Now, very important in determining the row spaces and column spaces from this is to recognize the ranks of the reduced row echelon form. The rank is any pivot of your reduced row echelon form. In other words, any leading one you see is a rank. So the rank of this matrix right here would be 2, since it has 2 leading ones. First part of the question asks us for the row space. For any row space of a reduced row echelon form matrix, we need to take all the rows that have a leading one, which in this case would simply be the first and second row. So the row space of A consists of the 2 vectors 1, 0, 1 and 0, 1, 0. What this means is that if we have any vector that is a linear multiple of this basis right here, then it would span the same row space that our matrix A spans. Pretty simple. Column space follows a similar idea. There is a slight difference to it though. We're going to go back to our reduced row echelon form. Again, we see we have a rank in the first row and the second row. First column and second column we have a leading one. So the first 2 columns are what we're interested in. However, we don't take the same 2 columns from our reduced row echelon form for the column space. We go back to our original matrix and we take the corresponding columns. So the first column corresponds to 1, 1, 2, 0. That'll be our first vector. And the second rank is on the second column, which would be 1, 2, 5, 1. And there is a basis for the column space. Again, any vector that is a linear multiple of these two vectors would belong to the same basis as our matrix A, same column space as our matrix A. The last subspace, which is the null space, requires a little extra effort. So I'm going to use a different paper right here. We need to use the same idea as one of my previous videos in which I taught the Gauss elimination method. So we need to solve our matrix right here, which was 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0. So to solve this matrix, we write down the equations x1 plus 0x2 plus x3 is equal to 0. So we treat it like it's a homogeneous system of equations. In the second row we have x2 equals to 0. No x1, no x2, no x3 in the next two rows. So these are the two equations we're dealing with. We can already tell, since there's a leading one in the first and second column, x1 and x2 will be leading variables, and x3 will be a free variable. Recall from my previous video that any free variable needs to be given a variable. So let's set it as t. To write x1 in terms of t, we would have x1 plus t equals 0, which means x1 equals to negative t. x2 will remain the same since it does not involve x3 or t, and x3 of course is equal to t. Now if we're to find the bases, we simply multiply t by x1, x2, and x3. So x1 includes t negative 1 times, x2 includes t 0 time, and x3 equals t once. We're basically looking at the coefficients of the t in this case. So the null space of A was t negative 1, 0, and 1.